It's my pleasure to introduce Dr. Yangang Liu. Dr. Liu is from Brookhaven National Lab, and he's a senior scientist there and a leader of the climate and process modeling group. And his scientific interests have been centering on atmospheric particle system. That include aerosol, cloud precipitation, and associated process, and interaction between all these particles. His research spanned over a wide spectrum of topics, including aerosol cloud physics, that's very much related to us, and turbulence, latent scatter radio transfer, remote sensing, and climate change. And his current research centers on the development of and evaluation of the cloud-related parameterization for model of various scale, from large ID to climate, global climate scale. So this is very close to what we do here, and will be very useful to us. And Dr. Liu has an amazing research academic record. His research has resulted in 102 peer-reviewed publications in prestigious journals like Nature, Nature GEO, and a physical review letter. And his work has been featured by Nature News, American Physics Society, and American Institute of Physics, American Geophysical Union, and some other medias. And his topic today is mainly about parameterization across all these skills. With that, please.
Thank you, Ray, and thank you for the invitation or nice introduction. And very nice to come here to, again, I think I came here about a few years ago, give a presentation on model evaluation. So as Ray, you mentioned, today I'm going to share some of my research on microphysics parameterization. It's really a great honor to share this research in this great institution that really are experts in modeling. I guess we start to talk about the giving a seminar here since last AGU. So it's been a while. We finally pick up a day, raining day. That's, I guess, what happened to people doing weather-related research. In any case, thank you very much for attending the seminar. So here's the outline of my talk. So I'm going to give a quick introduction about background. Especially, I'm going to introduce some of the main gaps which I think that exist in cloud microphysics parameterization. And then I will dive down into three major topics today. One is to try to discuss the possibility to using statistical physics as a foundation to build cloud microphysics parameterization. And the second one is to talk about the effects of turbulent and entrainment-mixing processes on cloud microphysical properties. And then introduce a new model we are developing now at BNL. My group is it's called particle resolved direct numerical simulation. And finally, I give a summary of my talk. So just some background. So like today, my topic is about cloud microphysics. And just give a very quick review about the importance of cloud microphysics. At the very beginning, probably before 1940s, people studying cloud microphysics really starting from their scientific curiosity, pure research, right? And then after that, and in the 1940s, when people starting to do weather modification, they found a seeding agent. Then weather modification became a major driver of cloud microphysics research. And as I guess most of you know this, in the 60s, people started to develop a climate model and the weather forecasting model, and they started to parameterize cloud microphysics, which is become a topic in modeling development. Of course, the 70s, that is cloud resolving modeling of clouds, also large area simulation modeling. So now I think, in my view, the four major areas that are converging toward each other regarding the understanding and the parameterization of cloud microphysics. And the converging actually makes the topic more interesting and probably more demanding. By that, I'm going to show some of the major models we are using to address atmospheric phenomena. As you know, atmospheric phenomena, because of turbulence, the other processes involved really complex processes, and that occurs over wide range of scales. Okay? Therefore, to address this process, we cannot use a single model. We have to use different type of models to address different problems. Here is a list of major problems. So starting from climate model and the numeric weather forecasting model, cloud resolving model, and large area simulation model, and the direct numerical simulations. Of course, they are simplified, idealized model type that's called parcel model. And probably with the exception of DNS, all of these models require parameterization of climate microphysics because the grid of the model is grid size much larger than the scales the microphysical process that actually occur. Okay? And therefore, to parameterize the microphysics, basically there are three types of parameterization development. One is probably just based on empirical relationships. That's the earliest parameterization. Another really, you run a very detailed microphysical model, then curve fitting the detailed model results, and then as a parameterization for larger scale models. The third one, which is try to derive the parameterization from first principles as much as possible. That's the area my interest in, and I'm going to talk about this topic. Basically, how we can try to derive microphysics parameterization from theory as much as possible. And by doing that, with the development of understanding microphysics, also the modeling development, including parameterization development, we can see over the history, we start with one moment scheme. That's basically at the very beginning, we just are interested to try to predict, for example, the water content. Right now, when people are starting to be interested in aerosol-cloud interaction, and also realize the importance of number concentration, particle number concentration, for example, drop number concentration. So right now, the most popular scheme probably is two-moment scheme. Right? That's in addition to liquid water content and drop number concentration. And as we know, with computer development, also we probably need the three-moment scheme, which is in addition to liquid water content and the drop number concentration, we also need another parameter that represents the spectral shape of size distribution. I call it the relative dispersion. Basically, relative dispersion is a standard deviation of size distribution divided by mean size. That's the parameterization I'm working on right now. So because of consideration of the spectral shape, but therefore, the further advancement of microphysical parameterization really bring the issue to the heart of the physics, of cloud microphysics. And this, by the heart, really refer to, probably know, that the spectral broadening and also reinitiation problems. And these two problems are all tied to turbulence. Here example. So the first one, the spectral broadening. So this is what do you mean by spectral broadening? That is basically observed droplet size distribution tend to be broader than the current theory predicted, or conventional theory prediction. Conventional theory predicted a very narrow distribution, but what we observed much broader. So this is a long-standing problem in cloud physics, and I think the key factor that are missing in the conventional theory is how to treat turbulence-related process to address droplet size distribution. So,
could you stop a little bit? Excuse me, please mute. Everybody have to mute on telephone. I think someone is making a typing noise or something. And please don't use, if you use speakerphone, it's definitely you have to mute. I think I can hear the echoing noise as well. Thank you.
Another long-standing problem, as we know, is reinitiation. And by the way, my talk today really focuses on warm clouds, okay, without evolving ice processes. And so we know in cloud physics, there's because condensation grows, the rate of growth decreases with droplet size, and the collection process increases with droplet size. But in the particles somewhere between 10 microns, 20 microns, and there is a dip, a minimum, or bottleneck. Some people call this basic valley of death. How, in order for ring to form, particles have to go beyond the droplet size around, say, 15 microns, right, radius. So, and this is a typical problem, how these so-called embryonic raindrops formed. There are some theories, like giant nuclei, and I think also not just me, people tend to think, and the major missing factors in conventional theory also relate to turbulence. Another major knowledge gap, I think, that's related to models, right? In terms of studying clouds, probably the best model right now is large eddy simulations. Right now, typical large eddy simulation grid size is about 100 meters. So we know the processes that actually important for microphysics are much smaller scales. That's much less than 100 meters. So therefore, there is a major scale gaps between, say, the smallest turbulent eddy that's about 1 millimeters in the atmosphere and about 100 meters LES scales. Therefore, what happens in these scales and their interactions with microphysics, we have very little knowledge of it because the limitation of measurements, also because the model development. So therefore, you can see all those three major knowledge gaps where I think we have, they are tied to turbulence, which in my opinion. So keep these three major puzzles or knowledge gaps in mind. So in the next, I'm going to introduce how some of the research I've been doing try to address these problems. The first one is regarding the parameterization. I guess often people think about parameterization is like a practical need because computational limitation. Actually, if you think about the problem harder, like parameterization, what parameterization do is parameterization really is try to account for collective effects of many smaller scale processes on larger scale phenomena. Right? If you think about statistical physics, it's basically trying to address very similar thing, right? Try to represent the large scale thermodynamic properties of the system in terms of statistical large ensembles of particles, so molecules, right, for a classical system. Here is an example of convection scheme, and also my research today, my talk is about droplet. So I'm going to try to see whether we actually can use statistical mechanics ideas to study droplet system. Basically, my talk consists in this two parts. One is how we are going to derive a most probable size distribution. That is basically I try to provide a theoretical foundation for the gamma function or Weber function that has been widely used in deriving microphysics parameterization for virtually all of the models we are using now. The second one is we try to introduce a new reinitiation theory, and also how we're going to use this new theory to derive our conversion parameterization. That's another process which needs to be parameterized in larger scale models. So, like I mentioned, in cloud physics or in parameterization development, you go through literature. These are the people tend to. These are the size distribution functions people tend to use, basically based on measurements. Right. The first one is Weber distribution, gamma distribution, log normal, and then there are some people use power law, exponential normal, and so today I'm really going to focus on the three ones: Weber, gamma, log normal. What's the theoretical? Is there any theoretical underlying this size distribution? That's basically I try to do. So back again is how we can, because of turbulence, therefore the clouds, the microphysics is really fluctuating a lot, and therefore the idea is very much like the statistical physics. We are not going to treat try to track individual droplets in cloud. That's almost impossible in reality. But we try to see whether, if we consider as this droplet as a system, whether we can actually derive a size distribution, right, for droplets. So this is kind of an analogy I listed here. Right? This is basically a molecular system. And starting from the very beginning, people realized the kinetics cannot explain observed thermodynamic properties, and people, Maxwell, Boltzmann, Gibbs, established statistical mechanics, right? And of course, with a great success. And for clouds, this is kind of an analogy, right? So I'm going to try by this analogy, I try to derive most probable distribution. By what do I mean by that? That is, consider a droplet system with a distribution low x, right? So the x, think about the x right now is just a variable which is related to the physical constraint of the droplet system. You can write down like this. Then you can define a spectral entropy, pretty much like the conventional Shannon entropy is related to the distribution like this. There is a prefactor that's ignored before the integrals. So you maximize this entropy, basically, to the system constrained by the previous two constraints. You will get, again, basically a distribution with respect to x, very much like a Boltzmann distribution for molecular system that respect to energy, right? This exponential distribution. But we know in clouds, many of these variables, like surface energy, mass, terminal velocity, you can think of, they are related to droplet size with the power law function. So although we don't know x, what x is, but I think we can have a pretty good assumption, but with this power law relationship. So the x, the conservation variable x, is related to the radius of droplets with this relationship. So you substitute this parallel relation to the exponential distribution, you actually get a distribution that is a Weibel distribution. Right? Therefore, this kind of making me think why. Let's go to these slides. So this is slides compare the three commonly used distribution form, right? Log normal, gamma, Weibel. The dots are measurements for clouds, rain, aerosols. And so each of the dots in these symbols here actually represent individual side distribution. Okay, you can see, and so the curve, this curve is corresponding log normal distribution. So if you're a log normal distribution, your curve is going to be followed like this. This Weibel and gamma, the dashed line gamma distribution. And these two is like two non-dimensional numbers. Okay? So you can see by comparing with measurements, clearly suggests and two things. One is either Weibel or gamma distribution describe the measurements better than log normal distribution. Also, another thing within the range of this, at least this data set, and the Weibel and the gamma are very similar. Right? They are very almost indistinguishable. Therefore, I think the maximum entropy, a principle applied to a system constrained by the two constraints I just listed, and provide a theoretical foundation for developing parameterization that really is based on gamma distribution. So the next topic really is about reinitiation and also autoconversion process. So as you know, autoconversion really is a process used in models that as a first step from cloud droplets to raindrops. Right? And like I said at the very beginning, I mean, people used to think autoconversion is just something people think of as a practical convenience. But right now, I think actually autoconversion is real process. It's not just a practical convenience. I'm going to show in the next few slides why I think that way. So, generally speaking, autoconversion is people tend to parameterize autoconversion rate as two functions, product two functions, P0 and T. So P0 I call is just for presentation purpose called rate function, and then there's the threshold function, right? That did basically characterize the steep of the very beginning of the process. And I mentioned earlier, and this is also works for autoconversion parameterization. Basically, they are educated against in the early days, and then later on, people use expressions that are basically deriving by curve-fitting detailed model simulations. Okay. And I mentioned the threshold function. The currently most used type is Kessler type, which basically the threshold function is a Heaviside function. Barrier type, there is T, threshold function is 1, and the Sundquist T is exponential like function. And all these empirical ones, they have empirical parameters here. It has unclear physical meanings, right? But if you can derive this autoconversion parameterization, at least we know the meanings, the parameters, or even eliminating some of the empirical parameters, tunable parameters in parameterizations. So, well, the first work I did actually try to derive the rate function, I call it P0. And basically based on a very commonly, widely known collection process. Probably a major pioneer in that is a Nobel Prize winner in chemistry, Lamior. He developed the collection theory for cloud droplets. So based on this picture, the autoconversion is basically a collection of cloud droplets by small raindrops. So you go through the algebra, so you actually can derive by applying this equation listed on the right-hand side. I'm not going through the details in interest of time, but people are interested can look at these papers. You actually can recover most of the existing empirical parameterizations by using different approximations. Here is an example. So the black, basically the black curve is the one derived from the theory. And the rest are those schemes are commonly still are used in most of the models, right? So you can basically catch the mean behavior. So with this, with knowing the rate function, and so the next step really is the threshold function. This is just an example for Kessler type parameterization, right? If you look at this equation, besides the rate function, you have the threshold function for Kessler type that is a Heaviside function. In this equation, you have a critical radius. Most of the parameterization use a prescribed critical radius. Right? But the idea is what I'm trying to do is see whether we can actually derive an expression for critical radius instead of prescribing, as most parameterization do. To do that, team up with my colleague, BNL colleague Bob McGraw, we developed a new radiation theory we call connected potential theory. It's kind of, if you think about, I mentioned the valley of death, just this cartoon to show the general idea about the theory. The theory is very much like what I just talked about droplet system. We try to look at the population and the system instead of as individual particles, as a conventional theory do. So if you think about it this way, so you turn around, actually the valley of death actually acquires the amount of life. It's very interesting. What happened is you can, again, I'm not going to go through the details. The idea is this theory is to consider within the system there are three processes that occur simultaneously. But these drops, one is collision coalescence, condensation, also evaporation in clouds. With this process in a dynamic balance, you actually can derive connected potential. The connected potential is a function of the droplet size, right here, right? So it's the increase first, and then reach a peak, then decrease. So therefore, if in nature, in cloud system, in order for ring to form, actually, you need to go through this barrier climbing process. Once you go over the barrier, then the rim start to form instantaneously, spontaneously. So we call that the radius corresponding to the connected potential peak as the critical radius. That's basically the general idea of this theory. But the nice thing about this theory, actually, if you go through it, you can derive the critical radius in the analytical expression. This expression is just shown here as a function of liquid content, that's L, and drop number concentration, that's N. Right? And so you can see from here, right? Then you actually can derive this. So this is very nice. So therefore, from now on, we don't need to prescribe a critical radius anymore. I actually have expression, theoretical expression to represent the connected potential, and to represent critical radius, I'm sorry. And with that, if we know the critical radius, we actually can modify the rate function to derive the threshold function, go one step further. What this is, by basically truncate droplet size distribution at the critical radius. By doing that, you actually can derive the autoconversion threshold function T here. Okay, and this, what interesting about this theoretical threshold function It is a function, basically two non-dimensional parameters. One is the ratio of the mean to critical mass of the droplet population. Another is the relative dispersion represented in sigma here. So you can see actually the different type of autoconversion parameterization really representing different values of the spectrum, different value of the relative dispersion. In other words, the width of the size distribution. So therefore, you basically varying the spectral shape of size distribution recover all the major types of parameterization people have been using in parameterizations. So I think this theory kind of provide a nice a theoretical foundation for most of the parameterization people use. Again, this is kind of whether this is theoretical work, where there are assumptions involved, how good this theory is. So because we derive a theoretical expression, this work is kind of evaluate the theoretical autoconversion threshold function by comparing with measurements. This is team up with some scientists, University of Wyoming. They have aircraft. On aircraft, they have in situ measurements of raindrops, cloud droplets, and also they have a radar. So each of the dots are from different cases of the clouds. The curves are derived from the theory with a different assumption of the spectral shape, just mentioned. And I think by defining the threshold here is about 90% a radar threshold, and you actually can derive this relationship as a function of drop number concentration. So this is the evaluation. So then this means the actual threshold function, radar threshold is also a function of drop number concentration, not empirical constant. People often assume in both remote sensing, also in model development. Although there are some scatter, I think this provides some kind of confidence to me at least in the theoretical derivation we have. Also provide confidence to us about the theory, because the theory just have not been widely accepted. So the next steps I'm going to talk about with the theoretical part in mind, and I'm going to talk about entrainment-mixing processes. And all these things related to, right? And we know the clouds are open system because the entrainment and detrainment of cloud air with environmental air. And so after entrainment, you bring in dry air in, the next step in the cloud is the turbulence is gonna mix the dry air. Then at the same time, cloud droplet is gonna evaporate. Some actually gonna grow by condensation, right? So I'm gonna talk about the turbulent mixing. So after entrainment, and so it will be a surprise to you. So the entrainment-mixing process can generate a very different droplet size distributions. Right? This is a cartoon shows the major types depending on the relative speed of turbulent mixing process and the droplet evaporation processes. And this part pretty much is dominant the paradigm we are using right now. We are pretty much assume most of the parameterization are developed is based on adiabatic assumption. This is the kind of droplet concentration is a constant, doesn't change when it's being activated. And it's like this. And so because ambient clouds most of them are open system, therefore there's really a very idealization. The next step really need to go through the paradigm shift, I think, is considered entrainment-mixing process of the dry air. And like I mentioned, depends on this relative value they call down common number, the speed of the two processes major process you can have, we call the homogeneous mixing. And this means the turbulent mix is very fast. Therefore, all the drops exposed to the same environment. Right? Therefore, you get the distribution form like this, relation between size and number concentration like this. On the other hand extreme, when the speed evaporation is very fast compared to a mixing process, you can get because inhomogeneous mixing, you actually get a distribution like this. And so the size doesn't change very much, but the drop number concentration vary a lot. And then, of course, after the mixing process, the partial count going up, then you actually end up, you get a distribution like this. So you can see you can have anything in between. So you, depending on the different type of mixing processes in cloud, you actually get all kinds of different distributions. Therefore, you would expect a lot of properties would be different, like radiated properties, and they're even whether the cloud is going to form precipitation or not. So these are the kind of theoretical argument you see in reality. This is measurements from aircraft measurements. And so you can see this is the example of homogeneous mixing. This is inhomogeneous mixing. And this is inhomogeneous mixing with subsequent essence. You can have all kinds of things, like not just in theory, in reality occurs as well. The question is for us, how we are going to represent this, this different mixing process in clouds. People have been trying to do this. Oh, this is another example. Like I said, LES right now pretty much not represent the mixing process in LES, in other models as well. This example, comparison between LES model results and the measurements, right? And so let's see, this work faster is a LES model we developed at DNR based on Wolf model. It's basically the LES model. This shows relationship drop number concentration, liquid or content. If you just see, this is from the measurements. Right? If you just compare these two, you can see, okay, the model catch the liquid, water content, the drop number concentration pretty well. Reasonably well, right? But if you look at using the diagram I just showed before, if you look at the relationship between mean volume radius versus liquid or content, you see the differences between measurements and the models. The measurements, like the measurement tend to show these clouds tend to be inhomogeneous type, right? Because the size doesn't change very much. Water content or number concentration varies a lot. But if you look at the model, really it's like homogeneous mixing type. Right? So that means, and it also makes sense to me because you just assume in LES, implicitly assume a homogeneous mixing type in LES. So people, like I mentioned, people started to think about how to parameterize or represent at least the different effects of different mixing types on cloud microphysical properties. Most commonly used diagram people proposed is called microphysical mixing diagram. It shows as this. Before I only show is like mean volume radius versus number concentration. But later on, people realize actually if you normalize by adiabatic value, corresponding adiabatic value, you can cover a lot of much more data sets than just by using the RV or N themselves. So the idea is this. So this, I just said, so for inhomogeneous mixing is like this, straight line, and this homogeneous mixing is like this. So the idea is, of course, the first one people think about is just use the slope of this curve, right, to represent different mixing type. And later on, we realized doing this is good measure, but there are much large scatter in that because it's not constrained by the inhomogeneous or the homogeneous mixing type. So if we propose a parameter we call phi here is defined as basically the angle of this one. Okay, so you can see depending on the value of this phi divided here, when you can cover all the mixing types. So when phi equals 0, that represents extreme mixing, inhomogeneous mixing. When phi equals 1, that's basically homogeneous mixing. So the phi 1, therefore you have a quantity that can have values anything between 0 and 1. Right. So once we propose this, and the next thing I mentioned earlier, the Dom count number. People have think about using the Dom count number to characterize the different mixing time from a dynamical point of view. But this is the Dom count number here. If you see the turbulent mixing time scale, it depends on the eddy size. So that's actually eddy size in cloud. There you can have a lot of different eddy size. It's very difficult to parameterize it. Therefore, Lehman 2009 have a very nice idea, actually, by proposing a transition scale. This is L star here. Basically, the transition scale is the eddy size that when the Dom count number equal 1, or another way, these two time scales are equal to each other. So, and then they use the transition scale as characterization of mixing degree. But a transition scale, because transition scale is a dimensional number, is not that great. And therefore, we propose in the paper that basically divided by divide by the Kolmogorov time, the scale, eta here. Okay? So basically make this non-dimensional. Therefore, actually, by doing this, a larger transition scale number basically indicates a higher degree of homogeneous mixing. So therefore, we have one parameters which we can use to represent all the different type of mixing. So the question is how we're going to develop a parameterization. So because the transition scale, we can know the transition scale in the model if we use a two-moment scheme. Therefore, you can think about the transition scale number is known in the model. Therefore, if we know the relationship between the homogeneous mixing degree, and then we can use that relationship to parameterize the mixing type. This is the idea. This is from the measurements. And this from cumulus clouds, stratiform clouds. So generally speaking, it's, as expected, these two parameters should be positively correlated to each other. And therefore, if we know the relationships, and then we can use it as a parameterization. But these measurements we know because the limitation measurements, they have relatively high sampling, lower sampling frequency. So in the clouds, a typical instrument right now is probably about covers somewhere between 10 meters, 100 meters, one sample. Right? So therefore, and this process I mentioned earlier, there are a lot of going on actually at a scale much smaller than even 1 meters. Right? Some process occurs with a scale about a millimeter. So how we are going to address the next question, which is the scales, basically sub-LES scales, the process that sub-LES scales. So by doing that, because of the limitation measurements, so I basically turn to developing particle resolve direct numerical simulation. Here, next few slides, I'm going to introduce the DNS model we are developing. Here's the idea. The idea is this model basically we try to resolve the smallest eddy possible. Therefore, the model resolution is going to be around 1 millimeter. Okay. At the same time, we try to simulate the real cloud phenomena as best as we can. We follow each motion of each droplet. This is kind of here, right? And so you can see just by these two figures, because of turbulence, even at the scales smaller than at sub-RES scales, there are a lot of things going on. The droplets move around in the clouds and change sizes. So this model really, and I think, can provide a lot of new understanding about the process that we don't have much understanding right now. That really is about, for example, I just talked about entrainment-mixing process, or another really thing I haven't had time to talk about is turbulence microphysics interactions. And because we don't know much about this, therefore we really don't have a good parameterization for it as well. So this is the equation. So the model, the DNS, really consists of three major packages of modules. One is fluid dynamics, which you're familiar with. Another one is microphysics, right? And then the droplet tracking. Basically, we track the motion with Lagrangians. The model is a combination of Lagrangian and droplet tracking the Eulerian fields. So here is the cases we have examined, and I'm going to show some results today. Is basically the cases represent the inertial fields of the cloud field. Right? The first one, the case one, really represent well-developed process. The clouds already well mixed with dry air in cloud, and this one really is kind of a try to represent the laterally mixing process. It's like you think about the edge of this. Right? You have clouds this side, the dry air this side, it's mixed like this. And the third case, really, we try to represent the cloud top process, which you have cloud like this and dry air above. Right? We try to represent to see are there any differences for these three different cases. Also, because of the model's DNS really idealized, therefore the larger scale forcing for DNS really is, there are two modes we are running right now. One is dissipation without forcing, so let the turbulence dissipate with time. Another, we have turbulence forcing at larger eddies to force the DNS, so maintain the turbulence field, larger scale turbulence field. Therefore, by combining these three cases in the two modes, we have 6 scenarios. So the next slide is going to show some results of the 6 scenarios. This is the first one is liquid oil content variation with time, and drop number concentration, mean volume radius, mean radius, standard deviation, relative variation with time. The different color really represent the 6 scenarios. So I guess it's hard for you to actually discern the differences between the different colors, but one message from this view graph I want to convey is there are significant differences between the 6 different scenarios and also different times. Okay? So therefore, you think about how am I going to represent this thing. This is all, by the way, they are all kind of caused by the different entrainment-mixing processes I mentioned earlier, because the DNS really is at the same level. Right? You can think about DNS at the same level.
Which ones are the blue scenarios from the previous page? The blue ones are obviously separating there. I was wondering which ones those are.
The blue one is case 1. It's like already well mixed.
Okay.
Yeah. So it's kind of think of the case 1 as like somewhere between the two. So the next step is I show the mixing diagram, right? So basically use normalized droplet volume versus normalized drop number concentration. It goes through the first one and to this one. You can see actually the figure collapse each other somehow, right? So if that means if you use a mixing diagram as people has been using, you actually do get an idea about the mixing process, different mixing processes. Right? But still, they are a large scatter. Again, this 6 plot represents 6 different scenarios here. And so think about what about the further one, the quantities people propose to parameterize the mixing types. One I mentioned is the slope parameter is proposed by that paper, Andrew Zach et al. In just 2009. Okay, that's the left figure. And the right-hand side is the result based on our homogeneous mixing degree. You can see, as expected, different colors represent different types of these 6 different scenarios. The symbols represent scenarios. Probably it's hard for you to see the symbols. But the idea is here, the message I want to convey, the slope parameter, because not constrained well by the 2 theoretical extreme mixing types. You will expect a larger scatter, therefore it's not that great as a parameterization. Right, this is shown here. But if our parameter, because constrained by the 2 theoretical mixing type, actually get much tighter relationships. This is the curve fitting. The correlation coefficient is almost it's about 0.9. It's pretty high here. So therefore, you can use this relationship without if we don't have a better one right now. I'm still working on it. As the first step to
When you're talking about turbulence, is environment turbulence or cloud-generated turbulence or both?
both. Yeah, the environment turbulence once you bring in cloud. Yeah, the cloud process also can generate. Yeah, like latent heat release or evaporation, they also generate. So therefore, can use this equation to parameterize to present the mixing type at least for two moment schemes. So this from here you can see roughly this is because the color represents time, right? So this is from the beginning is blue, end of simulation is red, right? So basically you can see from this figure also, the beginning of the mixing process, the mixing process tend to be more homogeneous compared to the later stage of this process. You can see this from the cartoons, basically like this. The reason is, one of the main reasons is the size. With time, the mean droplet size becomes smaller and smaller because of evaporation. Therefore, the evaporation time becomes smaller. So here is a summary. Basically, really is not a summary, it's a take-home message because I think because the need to consider turbulence and its interaction with microphysics, I think we just scratched the surface, right? But I hope I demonstrate the potentials of using ideas from statistical physics as a foundation for parameterization development. Another thing is the potentials of developing a unified parameterization to represent all different types of turbulent entrainment mixing process, which has been lacking now in most of the models, including LES. And there are a lot of potentials for DNS models. I just showed the potential to address the entrainment-mixing process. There are also potential for other processes. I think it's a very nice tool. And like in my opinion, the current stage of cloud microphysics, kind of early days of classical physics, and people have tried to establish kinetics, statistical physics, thermodynamics. Now we have the three pillars, very established pillars for classical physics. But for cloud physics, we don't, right? I think this is very much like that days. And what I talk about today, just scratch the surface. You can see my generalized approach is trying looking at like top-down, like statistical physics, and then bottom-up, like DNS, right? To just try to learn from each other. So the next, the following four things are listed here. Is, some of them I'm working on right now. Is try to just implement our parameterization for entrainment-mixing process and test it. And so far I can see, including entrainment-mixing, I haven't really talked about dispersion, relative dispersion right here. But once you move from 2 moment to 3 moment, you really need to consider that. That's a major challenge. Another topic I'm working on now. And also, right now I'm talking about the system really assume it's large, right? Because I'm only talking about most probable distribution. But we know clouds are actually small systems. Because of that, we will have scale dependence in the system. And therefore, we need to consider, the buzzword nowadays is scale-aware parameterization. So how we are going to develop a parameterization, different parameterization with the scale information we will integrate. Therefore, we probably have a different parameterization for AES relative to numerical weather forecasting models. The current DNS I show you is like 1 meter domain size, about 1 meter cube. It's really smaller than typical AES. So right now I'm working on trying to speed up the DNS to expand the domain size. Hopefully someday we're going to couple with AES. Therefore, we don't need to only address the problem with idealized simulations. With that, this is acknowledgement. Also, stop here. Thank you very much. Take questions.
Any question for Dr.
So what's the unit you can give for your experiment? You only give the temperature and the RH. What's the wind?
You mean the DNS?
Right.
Yeah. The wind actually is like it says, use the 2 modes of turbulence. So is using assume the turbulence mode, the turbulence. So basically the inertial condition, the turbulence is controlled by 2 main things. One is dissipation rate. So that's the parameters. Another is the size of the eddy, the main eddy. So we basically, in the paper, I can send you a paper, so that we have a scheme that basically determines the turbulence we are put in, drive the DNS, which is determined by dissipation rate and the eddy size.
Because turbulence you have different scale.
Yeah, that's what I'm saying. There are 2 things. One is the dominant eddy size, the large eddy size. Another one is the dissipation rate. So there are 2 parameters in it. Basically, it's kind of very similar to a Fourier spectral characterization of turbulence, but with only the major mode. That's the way we use.
So like a hurricane, right? Different type of cloud.
Yeah, very much. Only the
so
scale is much smaller. So that's why there is a forcing term. Yeah.
So like for hurricane, so we have different type of cloud. So based on this parameterization, you can judge which part is the homogeneous, which part is the inhomogeneous.
Yeah.
This is related to the environment shear.
Yes,
Here we're
yes.
basically turbulent.
If the microphysical parameterization in the model are two moments based. So that in other words, you predict in the model you predict water content and the number concentration. So that then you can, that's your first step. Then you use this parameterization as a next step to derive a new property that consider entrainment-mixing process. That's the idea. Because right now most of the parameterization are adiabatic based.
I think 1 meter grid size for DNS may be too large.
1 millimeter?
You used 1 meter, right?
That's the domain size.
Domain size.
Yeah, the resolution is 1 millimeter.
1 millimeter.
Yeah, yeah. That's why it's so computational demanding actually. Yeah, it is 1 millimeter. So we try to resolve all the turbulent eddies. Yeah, but the trade-off is domain size is not large enough. Yeah.
Any question from people on the phone, please? Any other question?
Yeah, no question.
Okay. Thank you very much.
Yeah, thank you very
Thank
much.
you for your attention.